Introduction, asking the biggest question, humanity's oldest question. For as long as human beings have looked up at the night sky, one question has echoed through every culture, every civilization, every age. Where did it all begin? The stars above us are silent, yet they invite curiosity. From ancient myths of gods creating the heavens, to philosophers imagining infinite worlds, to scientists using telescopes and equations, humanity has always sought the origin story of the cosmos. And today, through physics, astronomy, and cosmology, we have a narrative unlike anything ever told, the story of the Big Bang. What is the Big Bang? First, let's clear a common misunderstanding. The Big Bang was not an explosion in space. It was an explosion of space itself. Around 13.8 billion years ago, all the matter, energy, space, and time in our universe were compressed into an unimaginably dense, hot state, what physicists call a singularity. Then, in a fraction of a second, this state began to expand. That expansion never stopped, it continues today. The galaxies moving apart, the stretching of space, even the faint afterglow we detect as cosmic microwave background radiation, all of it is evidence of that ancient moment. Why it matters, you might wonder. Why should we care about something that happened 13.8 billion years ago? Because the Big Bang isn't just about the past, it's about us. The atoms in your body were forged in stars that only exist because of the Big Bang. The cosmic microwave background radiation is literally the universe's baby picture. By studying the Big Bang, we learn the destiny of the cosmos. Will it expand forever, collapse, or meet another fate? Understanding the Big Bang is understanding the origin of everything, the timeline of the universe. To make this journey clear, scientists divide cosmic history into key eras. 1. The Planck era, 0 to 10 seconds, the earliest instant where quantum gravity dominated. 2. The inflationary era, space expanded faster than the speed of light. 3. The particle era, matter and antimatter formed, battled, and mostly annihilated each other. 4. The era of nuclei, protons and neutrons fused into light elements. 5. The era of atoms, electrons joined nuclei, creating the first atoms. 6. The era of stars and galaxies, gravity pulled gas into stars, galaxies, and clusters. 7. The present and future, cosmic acceleration driven by dark energy. Each of these stages tells us not only where we came from, but where we are headed. Evidence for the Big Bang. Science is built on evidence, not belief. So, why do cosmologists trust the Big Bang theory? 3 pillars of evidence stand strong. 1. The expansion of the universe. In 1929, Edwin Hubble discovered that galaxies are moving away from us, the farther, the faster. This means the universe is expanding, so in the past, it must have been smaller and denser. 2. Cosmic microwave background radiation, CMB. In 1965, Arnaud Penzias and Robert Wilson detected a faint microwave signal coming from all directions in the sky. This was the cooled down afterglow of the Big Bang itself. 3. Abundance of light elements. The Big Bang predicted that hydrogen, helium, and traces of lithium would form in the first few minutes. Observations match these predictions almost perfectly. Together, these 3 lines of evidence make the Big Bang one of the most successful scientific theories ever proposed. A new way of thinking. The Big Bang doesn't just explain the past. It challenges our imagination. It tells us the universe has a finite age. Time itself had a beginning. Everything we see, the galaxies, the stars, even space and time, emerge from a single moment. This is not just science, it's philosophy. It reshapes how we see reality and our place in it. The Planck era, 0 to 10 seconds. The universe's story begins in the tiniest slice of time imaginable, the Planck era. Time elapsed 10 seconds, 0.001 seconds. Conditions: temperature above 10 Kelvin, energy density beyond comprehension. Here, the known laws of physics break down. Gravity, electromagnetism, the strong force, and the weak force, all the fundamental forces may have been unified into one superforce. But because we don't yet have a theory of quantum gravity, we cannot describe this instant with certainty. The Planck era remains the last frontier of physics, the place where relativity and quantum mechanics must meet. Inflation 10 to 10 seconds. After the Planck era, the universe underwent a mind-boggling growth spurt called cosmic inflation. In less than a trillionth of a second, the universe expanded faster than the speed of light. Space itself stretched, smoothing out irregularities and making the cosmos remarkably uniform. Tiny quantum fluctuations were magnified into the seeds of galaxies and clusters. Without inflation, the universe would be chaotic, with hot spots and cold spots everywhere. But thanks to inflation, the cosmic microwave background CMB looks nearly the same in every direction, with just the right amount of tiny variations to form stars and galaxies later. The quark gluon soup 10 seconds onward. As the universe cooled from unimaginable heat, it became a dense, seething plasma of quarks, gluons, electrons, and photons. Quarks are the building blocks of protons and neutrons. Gluons are the glue that binds quarks together. At this stage, matter and antimatter were created in almost equal amounts. When they collided, they annihilated, leaving behind pure energy. But for reasons not fully understood, matter had a slight excess over antimatter. That tiny imbalance is why anything exists at all. Without it, the universe would be nothing but radiation. The formation of protons and neutrons 10 seconds. By 1/1,000,000th of a second, the universe had cooled enough for quarks to combine into protons and neutrons. This was a crucial step. Protons positively charged would eventually form hydrogen atoms. Neutrons neutral would allow the creation of helium and other light elements. In other words, the nuclear ingredients of stars, planets, and life were forged almost instantly after the Big Bang. The first 3 minutes, nucleosynthesis. Between 1 and 3 minutes after the Big Bang, conditions were just right for nuclear fusion. Protons and neutrons fused into light nuclei. About 75% hydrogen, 25% helium, and tiny traces of lithium formed. Heavier elements like carbon and oxygen did not form, yet they would require stars. This era is known as Big Bang nucleosynthesis. It explains why hydrogen and helium are the most abundant elements in the universe today. The universe of light 10,000 years. At this stage, the universe was filled with a glowing plasma of particles and photons. But because electrons were free, light could not travel far. It scattered constantly, making the cosmos opaque like fog. During this time, radiation dominated the universe's energy balance. Matter existed, but radiation controlled the dynamics. Only after approximately 10,000 years did matter begin to outweigh radiation in importance. The cosmic baby picture 380,000 years. Finally, about 380,000 years after the Big Bang, the universe cooled enough for electrons to settle into orbits around protons, creating the first neutral atoms. This event, called recombination, changed everything. The fog cleared. Photons were free to travel through space without scattering. That radiation is what we now observe as the cosmic microwave background CMB. The CMB is the afterglow of creation. Detected today as faint microwaves, it provides a snapshot of the universe when it was just 380,000 years old. Quantum fluctuations to galaxies. Remember the tiny quantum ripples stretched by inflation. Those ripples became slight density variations in the CMB, tiny differences in temperature across the sky. Over billions of years, gravity amplified those differences, pulling matter together into clumps. Small clumps became stars. Larger clumps became galaxies. Networks of clumps formed the cosmic web, the vast structure of filaments and voids we see today. In other words, the reason the Milky Way exists, the reason Earth exists, is because of quantum jitters in the first fraction of a second. From fireball to cosmos, think about the transformation we've just witnessed in under 1 second to 380,000 years. A singularity expanded. Forces split apart. Quarks formed protons and neutrons. Nuclei fused into hydrogen and helium. Atoms formed, light broke free. The universe took its first portrait in the CMB. The stage was set. The universe was now a vast, dark expanse filled with clouds of hydrogen and helium gas. Gravity was ready to go to work, pulling matter together into the first stars. The cosmic story was only beginning. The dark ages of the universe, after the universe became transparent at 380,000 years, photons streamed freely, giving us the cosmic microwave background. But then came along a mysterious period called the Cosmic Dark Ages. The universe was filled with neutral hydrogen and helium gas. No stars had formed yet. Space was dark, silent, and cold compared to the fiery plasma before. This lasted for hundreds of millions of years. The only light came from the faint glow of the CMB, slowly fading as the universe expanded. But gravity was quietly working, pulling hydrogen into denser and denser clumps. These invisible ripples of matter seeded during inflation were about to ignite the first sparks of starlight. The first star's population 3. Around 100 to 200 million years after the Big Bang, the first stars burst into existence. Astronomers call them population 3 stars. These stars were unlike anything we see today. They were composed almost entirely of hydrogen and helium, no heavy elements yet. They were gigantic, many hundreds of times the mass of our sun. They burned hot and bright but lived short lives, just a few million years. When they exploded as supernovae, they created the first heavy elements, carbon, oxygen, iron, and more essential ingredients for planets and life. Without these first stars, the universe would have remained chemically barren. The birth of galaxies, as stars formed, they gathered into clusters. Gravity pulled clusters into larger systems, the first galaxies. By around 400 million years, galaxies were already forming. Some were small and irregular, while others grew into massive structures. The Hubble Space Telescope has captured light from these early galaxies looking back more than 13 billion years. And with the James Webb Space Telescope JWST, we are now seeing galaxies even closer to the dawn of time. These discoveries confirm that the universe was busy building structure very early. Reionization, lighting up the cosmos, the first stars and galaxies didn't just shine, they transformed the universe. Their intense ultraviolet light ionized the surrounding hydrogen, breaking atoms apart into protons and electrons again. This period, called the Epoch of Reionization, happened between 500 million and 1 billion years after the Big Bang. Before reionization, the universe was like a foggy night. After reionization, it became clear, allowing light to travel vast distances. Thanks to this, the universe we see today is transparent, and starlight fills the cosmos. The cosmic web, as galaxies grew, they didn't distribute randomly. Instead, they formed along gigantic filaments of matter, leaving vast empty regions called voids. This structure is called the cosmic web. Filaments, long chains of galaxies and dark matter. Nodes, dense intersections where massive clusters form. Voids, enormous empty bubbles of space. Computer simulations, like the famous Millennium simulation, reproduce this web, showing how galaxies trace the skeleton of dark matter across billions of light years. The cosmic web is one of the most awe-inspiring patterns in nature, a universe-wide network connecting everything. The role of dark matter in galaxy formation. Dark matter played a crucial role in shaping galaxies. Without dark matter, ordinary gas would not have clumped fast enough to form stars and galaxies in time. The universe would still be nearly uniform. Dark matter created gravitational wells where gas could collect. It acted as scaffolding for galaxies. In fact, every galaxy, including the Milky Way, is embedded in a dark matter halo. Without it, galaxies could not exist. The first black holes, the first massive stars, also left behind black holes. Some of these black holes merged and grew, becoming the seeds of supermassive black holes found at the centers of galaxies. Even in the earliest galaxies we've observed, giant black holes were already present, billions of times the mass of the Sun. How they grew so fast remains a mystery, but their influence on galaxies shaping their stars, gas, and evolution is undeniable. The Milky Way's early story, our own galaxy. The Milky Way began as one of these small early galaxies. Around 13 billion years ago, it was just a modest cluster of stars. Over time, it merged with other protogalaxies, growing larger and larger. Today, it contains over 200 billion stars, countless planets, and one supermassive black hole at its center. When we look at the oldest stars in the Milky Way, we are peering back to those ancient times when the galaxy itself was young. The Great Transformation, by about 1 billion years after the Big Bang, the universe had changed dramatically. Darkness had given way to starlight. Galaxies had begun to cluster together. Heavy elements had been forged, paving the way for rocky planets. Black holes had taken their place as engines of galactic evolution. The cosmos was no longer a simple soup of hydrogen and helium. It was a dynamic, structured, living universe. The foundations of everything familiar: stars, galaxies, planets, life had been laid. The growth of galaxies. After the first billion years, the universe entered a period of steady growth. Galaxies began merging, colliding, and evolving into more complex structures. Small galaxies combined to form larger spiral and elliptical galaxies. Star formation accelerated, filling galaxies with billions of suns. Supernovae enriched the gas between stars with heavy elements. Every time galaxies merged, they reshaped one another. Some spirals transformed into massive ellipticals. Others triggered bursts of star formation, lighting up the cosmos with brilliance. Galaxies became the engines of cosmic evolution. The formation of galaxy clusters. As billions of years passed, galaxies themselves collected into larger groups, galaxy clusters. A cluster can contain hundreds or thousands of galaxies, bound together by gravity. The space between them is filled with hot gas, glowing in X-rays. Dark matter holds clusters together, forming the backbone of the cosmic web. The largest clusters are superclusters, stretching hundreds of millions of light-years across. The Milky Way is part of the Laniakea supercluster, a massive structure containing 100,000 galaxies. In the grand architecture of the universe, clusters are the cities, superclusters the continents, and the cosmic web the map of it all. The life and death of stars. At the heart of galaxies, stars continue to be born, live, and die. Their life cycles shape everything around them. Small stars like red dwarfs burn slowly and live for trillions of years. Medium stars like the Sun shine for billions of years, then expand into red giants before shedding outer layers as planetary nebulae. Massive stars live fast and die young, exploding as supernovae, leaving behind neutron stars or black holes. Supernovae are especially important because they forge heavy elements like gold, uranium, and platinum. Without these cosmic forges, Earth's crust, oceans, and even our blood rich in iron would not exist. As the saying goes, we are stardust. The creation of elements. The Big Bang only made hydrogen, helium, and a dash of lithium. But the stars did the rest. Carbon, the basis of life, is formed in the hearts of dying stars. Oxygen for breathing and water comes from massive stars. Iron in our blood and the Earth's core is forged in supernovae. Gold, platinum, and rare elements are born in neutron star collisions. The periodic table of elements is really a record of cosmic history. Each element tells the story of where it was born: in the fire of stars, in the collapse of giants, or in the crash of neutron stars. The formation of planetary systems. As stars lived and died, they left behind enriched clouds of gas and dust. These clouds became nurseries for new stars and new planetary systems. Disks of gas and dust swirled around young stars. Dust grains stuck together, forming pebbles, then planetesimals. Gravity pulled planetesimals into planets. Some planets became gas giants like Jupiter. Others became rocky worlds like Earth. Asteroids and comets carried water and organics to young planets, seeding the conditions for life. Planetary systems turned galaxies into cradles of possibility. The birth of our solar system, about 4.6 billion years ago, in one corner of the Milky Way, a star was born from a collapsing cloud of gas. Around it, planets began to form. The central star became the Sun, the source of light and warmth for life. Inner rocky planets formed: Mercury, Venus, Earth, Mars. Outer giants formed: Jupiter, Saturn, Uranus, Neptune. Countless asteroids and comets filled the leftover spaces. Among these worlds, one planet stood out: Earth. The making of Earth was shaped through fire and bombardment. Early Earth was molten, with oceans of magma. Collisions with asteroids delivered water and organic molecules. A giant impact with a Mars-sized body created the Moon. Over hundreds of millions of years, Earth cooled, oceans formed, and continents took shape. Earth became a stable, life-supporting world, a rare jewel in the cosmos. The spark of life, around 3.524 billion years ago, life began on Earth. The details remain mysterious, but possibilities include lightning striking chemical-rich pools, deep-sea hydrothermal vents providing energy, comets delivering organic molecules. Whatever the spark, simple cells emerged. Over billions of years, evolution transformed them into plants, animals, and eventually, humans. Every living thing on Earth carries the legacy of that cosmic chain, from the Big Bang to starlight to DNA. Humanity looks back. Fast forward to today. Out of all the stars and galaxies, one species, humanity, developed the ability to look back at the universe's story. We built telescopes, launched spacecraft, and developed theories that let us peer across billions of years. Through science, we discovered that our atoms were made in stars, that our planet formed from ancient dust, that the universe itself had a beginning. We are not separate from the cosmos, we are the cosmos, made self-aware. The cosmic perspective, from the first galaxies to the rise of life, the universe's history is one of transformation. Hydrogen and helium became stars. Stars created elements. Elements built planets. Planets gave rise to life. Life gave rise to minds that could ask, where did it all begin? In this perspective, every human life is part of a 13.8 billion year journey. We are stardust, children of galaxies, storytellers of the cosmos. The expanding universe. In 1929, astronomer Edwin Hubble made a groundbreaking discovery. Galaxies are moving away from us, and the farther they are, the faster they recede. This revealed that the universe is expanding. Space itself is stretching, carrying galaxies apart. If we run time backward, all galaxies converge to a single point, the Big Bang. But the expansion also raises a profound question: what is the ultimate destiny of the universe? Gravity versus expansion. For decades, scientists debated whether the universe would 1. Slow down and collapse in a big crunch. 2. Expand forever, gradually cooling into darkness. 3. Balance perfectly between the two, reaching a big freeze. The outcome depends on two things: the amount of matter, both visible and dark, the mysterious force driving expansion, the discovery of dark energy. In 1998, two teams of astronomers studying distant supernovae made a shocking discovery: the universe's expansion isn't slowing, it's accelerating. Some unknown force is pushing galaxies apart faster and faster. We call it dark energy. Dark energy makes up about 68% of the universe. Its nature is still unknown. It could be a property of space itself. It determines the ultimate fate of everything, possible futures of the universe. Depending on how dark energy behaves, the universe may face several possible fates. The Big Freeze, heat death. If expansion continues forever, galaxies will drift apart. Stars will burn out. Black holes will evaporate. The universe will fade into eternal darkness. The Big Rip. If dark energy grows stronger, it could tear galaxies, stars, planets, even atoms apart. In trillions of years, space itself may rip apart. The Big Crunch. If dark energy weakens and gravity wins, expansion could reverse. The universe might collapse back into a singularity. This could lead to a new Big Bang, a cyclic universe. The Big Bounce, some theories suggest a repeating cycle: expansion, collapse, rebirth. Our Big Bang may not have been the first or the last, the end of stars. Regardless of which fate awaits, stars will not last forever. In about 5 billion years, our sun will expand into a red giant, engulfing Mercury and Venus, possibly Earth. White dwarfs, neutron stars, and black holes will be all that remain. Over trillions of years, even they will fade. The universe is a grand story, but every story has an ending. Humanity's place in the story, even though the universe will outlive humanity by unfathomable time scales, our presence is meaningful. We are a way for the cosmos to reflect on itself. We have traced our atoms back to stars, our planet back to dust, our story back to the Big Bang. As Carl Sagan said, we are a way for the universe to know itself. In this vast, expanding cosmos, we are small but not insignificant. The philosophical horizon, the fate of the universe, is more than a scientific question, it is a philosophical one. Does the universe have a purpose? Is there meaning in cycles of creation and destruction? Are there other universes beyond our own? The answers remain unknown, but the questions connect science to something deeper: the human need to understand our place in the cosmos. The ongoing journey of discovery. Though we may never see the universe's ultimate fate, we are living in a golden age of discovery. Telescopes like Hubble and James Webb let us see billions of years into the past. Particle accelerators recreate conditions of the early universe. Missions to Mars, Europa, and beyond explore whether life is a universal story. Every discovery brings us closer to answering the ultimate question: what is the destiny of the cosmos, the universe as a story? From the first spark of the Big Bang to the last flicker of starlight, the universe is a story, one still being written. It began in fire. It grew into galaxies. It gave rise to life. And it may end in silence. But in the brief moment of cosmic time we inhabit, we have the gift of awareness. We can look back 13.8 billion years and imagine billions more ahead. And that may be the most beautiful fact of all. In the grand universe, the story includes us. And that brings us to the end of our journey through time. From the birth of the universe in a single instant of fire and light, to the rise of stars, galaxies, planets, and life itself. The universe is vast, mysterious, and ever-changing. But in the middle of all this cosmic drama, one truth stands out: we are a part of this story. The same atoms forged in stars billions of years ago are now within us, asking questions about where we came from and where we are going. If you enjoyed this journey through the cosmos, don't forget to like this video, subscribe to the channel, and hit the bell icon so you never miss our next adventure into the mysteries of space. And now I'll leave you with a thought. The universe is still expanding, still evolving, and its story is not yet finished. Together, let's keep exploring, learning, and wondering. Because in the end, we are the universe looking back at itself. Always look up for and expand your imagination.